Good afternoon, everyone. I'm Michelle Sanner. Today, we are going to be talking about the different physical properties that are affected by the forces between molecules, those intermolecular forces. So the first property that I'd like to discuss is boiling point. And as you recall, boiling point is the temperature at a standard pressure, so it's just regular pressure, where a liquid is converted into a gas. So this is a physical change. And what that means is that no bonds are broken, no new bonds are formed, no bonds are rearranged. So it's taking a substance, like for example, water, and just simply separating those molecules from one another in order to change them from a condensed phase, like a solid, or like a liquid, in this case for boiling point, into a more dispersed phase, in this case, a gas. So let's take a look at the model and see what's happening. So this is a simulation, University of Colorado Boulder, and I can put any sort of molecule in here. Here's water, for example. As I apply heat, starting with a liquid, I can heat up this compound. As you see, the forces between the different molecules are overcome enough that those little water molecules at the top can start kind of flying off into space. And those are becoming gases now. Those are starting to occupy three-dimensional space as opposed to settling in that finite volume that liquid has. Similarly, if we cool it down, we can start to see those molecules slowing down, their kinetic energy decreases, their intermolecular forces are starting to become more of a factor as they get closer and closer together. They become held together better and better and better. And if I were to continue cooling, I would be able to go from gas down to liquid and then into a solid. So there's an example of what something looks like when it undergoes boiling by applying heat, causing those liquid molecules to separate into spacious gas molecules. But what's important to understand is there's no bonds being broken or formed here. That, if I pause, each of these little individual molecules of water is still a water molecule. So this is an example of a physical change. We're not breaking the bonds between hydrogen and oxygen to form hydrogen gas and oxygen gas. We're just taking the individual molecules of water and separating them from one another. So physical change, no bonds are being broken or formed. What's happening at the molecular level is that there's enough energy applied to the substance, to this liquid, to overcome those intermolecular forces between the molecules and allow them to spread out. As the strength of various intermolecular forces increase from London dispersion to dipole to hydrogen bonding, we find that the boiling points of those substances also increase. So intermolecular forces directly correlated to boiling point. The stronger the intermolecular force, the higher the temperature of the boiling point will be. So let's talk about melting point. Now, this is where the energy that it takes to convert something from a solid form to a liquid form. So it's the temperature at a standard pressure in which solids are converted into liquids. It's also a physical change, once again, meaning that no bonds are broken or formed. So let's take a look at what happens when I go from a solid, and I'll use a different molecule this time, to a liquid. So I have a solid, my molecules are vibrating, they have motion, albeit very small particle motion. But as we turn up the heat, the energy increases, the spacing between the particles gets larger as the intermolecular forces are overcome by this increased heat. And my molecules are now more free to move around and to spread out in the container. I'm still looking at argon molecules here. I'm still looking at individual atoms of argon, right? But their spacing is different. The forces with which they're held together are different. But again, no bonds are broken or formed. Let's look again at something like oxygen. So starting at a solid, I can apply heat and my molecules will start to separate from one another without breaking the bonds. If you take a look at any individual oxygen gas molecule there, I'll pause, and you can see there's still two oxygens bonded together here. So the molecular structure is still the same. It's no bonds are broken, no bonds are being formed, but the spacing changes as we are able to overcome those intermolecular forces by applying heat. So like I said, this is a physical change, meaning that no bonds are broken, no new substance is created. And like boiling point, melting point occurs when there's enough energy applied to a substance to overcome those intense intermolecular forces that occur in solid spaces of matter. Like boiling point, melting point also increases as intermolecular force increases. So molecules that are polar, that have dipole-dipole interactions, are going to have higher melting points than those with just London dispersion. And then ones that include intermolecular forces of hydrogen bonding will have the highest melting points relative to those with just dipole-dipole or London dispersion forces. Another property that's affected by intermolecular force is a property called cohesion. So cohesion refers to a substance's ability to attract to itself. So in this case, I have an example of cohesion in the water molecules on this spider web. Something about water's polarity, in fact, its dipole, allows it to have strong intermolecular forces that hold the water molecules to one another. They are cohesive. The idea of water attracting to water refers to the concept of cohesion. So cohesion increases also as intermolecular force increases. So as as you move from London dispersion through dipole-dipole and then H bonding, and you increase the strength of those intermolecular forces, the cohesive forces increase as well. So once again, directly correlated to intermolecular force. Next, we're going to look at the forces of adhesion. So adhesion is similar to cohesion, but in this case, it refers to a substance's ability to attract to another different substance. So the example of adhesion in this file here would be the water attracting to the spider web. So adhesive forces are also intermolecular forces. They are forces that exist between molecules. And they are, if you think about it, what an adhesive is, it's like a glue, something that sticks to something else. And adhesive forces do just that. One substance's ability to stick to a different substance or adhere to it is called adhesion. Like cohesion, as you increase the intermolecular forces and you move from London dispersion to dipole-dipole to H bonding, the strength of the intermolecular forces increase, and so too does the strength of the adhesion. So this is the third property that's directly related to IMFs. The last property that I'll talk about is called surface tension. And you've probably all seen like little examples of these little water bugs, and they can kind of skeet across the water and they don't fall in because there is a force that holds the water molecules together at the surface. So surface tension is a measure of the force that holds the surface liquid together at its surface. So it measures the amount of inward force that would need to be applied or would be required in order to break it. And the weight of a small bug like this does not apply enough force to break those strong intermolecular forces between the water molecules. And so thus they're able to skeet along the top of the water. So surface tension, a measure of the inward force that would need to be applied in order to break the IMFs that hold surface molecules close together. As you can imagine, molecules with higher intermolecular forces acting upon them, like dipole-dipole interactions and H bonding, are going to have much higher surface tensions. And so here's a little visual. You can see what's going on pretend each of those balls is a water molecule, and those water molecules are attracted to one another very strongly because of the H bonds that occur in water. And so things are able to, settle on the top of it, like these little water bugs here. They don't have enough weight to apply enough force down in order to break the surface tension. So this is the fifth physical property that is affected by stronger intermolecular forces. So one thing that's really important to understand is that all of these properties that we discussed for a substance, its boiling point, its melting point, adhesive properties, cohesiveness, surface tension, all of these are physical properties. They're all things that involve no change in the bonds or the identity of the substance. So whenever that you are separating molecules, breaking apart those intermolecular forces, perhaps we shouldn't use the language of breaking and forming because that refers to bonds. So we tend to say with intermolecular forces that with enough energy applied, we can disrupt or overcome the intermolecular forces with additional energy. So for example, boiling water, this is not there are no bonds broken when you boil water, The forces holding two water molecules together are simply overcome with the application of enough energy and allow them to spread out away from a condensed phase. So let's take a second and compare physical versus chemical changes. In bonds, when you have a chemical change, that means that bonds are broken or formed. So chemical changes refer to the breaking and forming of bonds. Physical changes, however, do not involve bonds. Instead, they involve intermolecular forces, which are overcome and allowing molecules to separate from one another. And what is it happens in terms of identity? Well, in a chemical change, new molecules are formed when you undergo a chemical reaction. Bonds are rearranged, bonds are broken, bonds are reformed, and this involves a change in the identity of a substance. However, in a physical change, the identity of the substance does not change. Only its phase of matter changes from solid to liquid to gas, depending. And what type of forces are we talking about? Well, in chemical changes, we are changing the forces of chemical bonding. So that sharing of electrons that atoms tend to do when they form bonds. However, on the opposite side, physical changes involve a force of intermolecular forces. So the idea that intermolecular forces are overcome with enough energy. So I hope that you have a couple good examples about the difference between physical and chemical changes, and that you'll be able to apply and predict what types of boiling points, melting points, adhesive properties, cohesive properties, and surface tension that elements might have based on their type of intermolecular forces. Next time we meet, we're going to practice predicting the boiling points and the melting points and other properties, other physical properties of matter based on the chemical formula, its Lewis structure, and its geometry, which determines its overall polarity. So I hope you're doing well and that you're having a great day, and I will see you soon.